Okay, welcome to this lesson about differential equations. So to start with, I'm going to give you a quick question for you to have a think about. So you've got dy by dx is equal to 3x squared minus 9x. And the question is, what is y? So just have a very quick think about how you would find y if you were given that equation. Okay, so the way that we would do that is we would integrate the expression. So we would integrate 3x squared minus 9x. We'd integrate that with respect to x, which would give us x cubed minus 9 over 2 x squared plus c. And that is what we would put as equal to y, because if you integrate dy by dx, you get y. So that's a question that you can already have solved before you came and watched today's video. But what about the second example? What about if you have a look at this one? Is this something that you think you can solve at the moment? If so, how would you do that? And if not, what would the issue be? So have a quick think. Okay, not giving you much time there, but possibly you've spotted that because we have the y on this side, if we were to simply integrate the expression on the right hand side, we would actually be integrating something with y's and x's in, which we haven't done. We don't know how to do that. All we know how to do is how to integrate an expression with x's in with respect to x and y's with respect to y, so separate. Okay, so we are actually going to think about today looking at solving. Just going to change this slightly. We're not going to do the right, but we are going to do the solving of differential equations. And the good news is, if you manage to, in that short space of time I gave you to think about it, if you manage to get that very first question yourself, then essentially you have already solved a differential equation. So that's good news. Okay, so what is a differential equation? So here's your definition. It's an equation that involves an expression which is a first order derivative, such as dy by dx. So because that one in the very first slide had dy by dx equals in it, that made it a first order differential equation. If you have that second order derivative, it would be called a second order differential equation. Okay, so an expression that looks like this, dy by dx is equal to 2x, that is what we call a first order differential equation. And when we say the word solve, what we actually mean by solve is we mean make it y equals. Okay, so whenever you're looking at solving a differential equation, you are trying to make it y equals. You're trying to get rid of that first or that second order derivative. Okay, and we've established already that the method that we use by solving is that we use integration. Now, if we take that example specifically there, i.e. that dy by dx is equal to 2x, so this one up here, we know we can integrate that, and that would give us an expression y equals x squared plus c. You've got that constant there at the end. So actually, when you solve that differential equation, you don't get what we call a unique solution. You don't get just one answer. What you actually get is a whole family of solutions, a family of curves. Okay, and that's what we call, where you've still got that constant c in it, we call that the general solution of the differential equation. Okay, now if you wanted to narrow your answer down further, you would need to be given what is called a set of boundary conditions, such that you're told that the curve goes through x as 1 and y as 2. What we would do then is we would do the integration as we've done before. We would get this general solution, okay, and then we would substitute in what we call those boundary conditions. Okay, and that would give us a value for C, which we can then sub into the expression to get our final equation. And because we know what C is, we would call that the particular solution. Okay, so the general solution is where you've still got the C in. The particular solution is when you then have the boundary conditions and you've subbed those in. So let's look at an example, and what we're going to do to start with is we are going to just look at the general solution. Okay, I'm not particularly good at let's put all the steps up in one go, then I don't have to tap through. Perfect. Okay, so the question is, find the general solution to this differential equation. Now this looks a little bit like the one we had right on the second slide, because we've actually got something with x's and y's in, okay? And we have already established that we can't simply integrate that right hand side because it's got a mixture of x's and y's in. So what we need to do is we need to separate the x's from the y's. Let me just write that down. What we're going to do to start with is we are going to separate. Okay, so the way I'm going to do that is I am going to factor that y out. That gives me x plus 1 in that bracket. Okay, and then we not only want to separate the x's from the y's on the right hand side, but essentially we want to separate it on the left hand side as well. Okay, now we've talked about before the fact that dy by dx is not a fraction. Okay, however, it does behave like a fraction in some circumstances, and what I mean by that is I can essentially take the dx from the bottom and multiply it up onto the right hand side, giving me x plus 1 dx on the right hand side. Okay, that would leave me with dy on the left hand side, and what I would choose to do is I want the y that's up here to go over onto the left hand side as well. So I'm actually going to have to divide. So we get something that looks like 1 over y dy equals x plus 1 dx. Now, you should never just leave that written as it is, because technically, as I've written it now, it's not a mathematically correct statement because I've separated it like a fraction, and it's not a fraction, okay, the dy by dx. So I'm going to write the next step on the same line as well, and you can see over on the right hand side that step 2 is to integrate. Okay, so I've separated, now I'm going to integrate. I've run out of space a little bit, so what I'm going to do is just do it in a different colour so you can clearly see I've put in the integration symbol on both sides. That now makes it a mathematically correct statement, the fact that I have put integral of 1 over y dy is equal to the integral of x plus 1 dx. Okay, then I'm going to do that integration, so that would give me ln mod y on this side, and it's going to give me half x squared plus the x plus a c on that right hand side there. Okay, so I've done step 1, I've separated to get all the y's and the dy on one side and all the x's and the dx on the other. I've then integrated it and I have this expression. Okay, I should try and make it y equals, make y the subject. It doesn't always ask you to in a question, in which case you don't necessarily have to, but you should get into the habit of making it always y equals. So the way I know I'm going to need to do that is I need to get rid of the ln on the left hand side, the ln, which I will do by taking the exponential of both sides, so raising it as e to the power of, okay? And that would give me y on the left-hand side, and then e to the power of that whole expression. So let's write that out. So I get y equals e, this is where it's a bit tricky because it's small, to the half x squared plus x plus the c. So all of that goes in the power together, okay? Now we can tidy that up a little bit further, okay? What we can do is we can use our indice rules, and we know that when you have additions in the powers, in the indices, the rule we're actually using, let me write it onto the side, is we are using the fact that if you've got e to the x plus y, that's the same as e to the x times e to the y. That's the rule I'm using, okay? So we can make this y equals e to the half x squared plus x times e to the c. Now remember, c is just a constant, so e to the c is also just going to be a constant. So to tidy this up, I'm going to let capital A be e to the c. It could be any letter, but convention is we just use a. And that then gives me my final answer of y equals e to the half x squared plus x. Can't do anything with that really. And I have forgotten, go back one step, I've forgotten my a. Oh dear, 1 second. So let's go back to that. So I wanted it to be a. Oh, I'm not going to fit that in. Bear with me, let me rub all of that out on that line. Oh, and the line above. Okay, so that line above was e to the half x squared plus x times e to the c. So we get e, and we've let the e to the c be a, so that is a, and then you've got your e to the half x squared plus x. I'm going to put that in a little red box so you can see what my final answer is. Okay, so there were 3 steps to that process. Step 1 was to separate, so to get the y's and the dy on the same side, and the x's and the dx onto the other side. Then we integrated both sides, the left with respect to y, because you have the dy, the right with respect to x, because you have the dx. Step 3 is essentially you trying to make it y equals. So because I love a rhyme, if step 1 is separate, and step 2 is integrate, then step 3 is manipulate. Okay, there we go. Okay, let's try just one more example. So here's just a bit of a summary of the information that I have already said. So the idea is to separate the variables, get all of your function of y, so all the y terms and the dy, put that on the same side as the dy, so that's usually on the left, okay, and then the function of x with the dx, okay, so we are separating it. And it just says here, again, to avoid writing it once you've separated it without the integration symbol, because technically it's not a mathematically correct statement. So once you've done that separation, pop your integration symbol on. Okay, let's have a look then at this example. So again, we've got find the general solution to dy by dx is equal to x plus 2 over y. Okay, so step 1, remember, was separate. Okay, so what we're going to do is we are going to take the y that's down there, and I'm going to multiply it up onto the left hand side, so it becomes y dy equals, and on the right hand side you've got the x plus 2 dx. Okay, and as I said before, we want to have the integration symbols there so that it's mathematically correct. Step 2 is then that we perform that integration. Okay, and remember that we integrate the left with respect to y because it has dy, so that becomes a half y squared. Okay, and then the right hand side is equal to a half x squared plus 2x plus the c. You might be wondering at this point why I've only put the c on one side and not on both sides. So, in theory, it would make sense for me to put, for example, let's just use a different letter. Let's use C1. So put constant 1 on the left hand side and put a constant 2 on the right hand side. Then what I could choose to do is to make this side, to bring the constants together, C2 minus C1. Now, since constant 2 is a constant I don't know and constant 1 is another unknown constant, if I subtract them, I'm left with another unknown constant. So essentially what we're doing by just putting it on the side with the x's is we are putting a constant of integration on both sides, but then in theory we're pulling them over to one side because they're just values that we don't know. So let me rub that out now. Okay. So we are going to stick with just putting the constant there on one side. Okay, step 3 then, once we've done our integration, is we are going to manipulate. It doesn't say in the question, put it in the form of, but let's have some good practice of doing it. So if I double everything, I get y squared is x squared plus 4x. Then you can either call this 2c, or again you can call it a different constant. Maybe you want to call it k. It's just an unknown constant. Okay, we'll deal with that later. And then to make it y equals, we want the square root of everything on the right hand side, and I'm just going to put that, instead of doing square root, I'm going to put it all to the power of a half.